Like I was just asked to introduce the speaker. I didn't have the time to look up his CV, but I sort of remember a few things. So actually, my first year in graduate school, I started by taking Dimitri's classes and then came for him. So Dimitri has spanned a monumental breadth of topics, of which he has written seminal textbooks. He's still very active in research and writing. Has received plenty of distinctions, all sorts of awards. Control System Society from the IEEE award is the latest one. Member of the National Academy of Engineering, and so on and so on. So he's been working on reinforcement learning back, I guess it was about 25 years ago. So at that time, we were even working together. Yeah, he's still very active in this. So I understand he's going to tell us today about some insights that are captured in his very recent book. So,
Okay, it's my great pleasure to give this talk in person. I think the last time I gave a talk in person was 5 years ago, right in this room. And so it feels nice to be back. What I'd like to talk about today is my new book. And it just came out a few months ago. And I'd like to give a summary. And that's the title of the book over there. And the book is short and it relies on visualization, and its mathematics are reasonably rigorous, but there's a lot of mathematical detail that's left out, and it's contained in these other books that you see here. So the objective is to develop a new view of reinforcement learning and its relations to the subjects of control system design, model predictive control, adaptive control, and also discrete optimization, like integer programming and things like that. It's a very, very general framework couched on the methodology of abstract dynamic programming. And it is also inspired by the AlphaZero chess program, which has made a lot of headlines. So I'm sorry, I'm going to sit so that I'll be able to point also on my screen. I'd like to start with these two remarkable programs, AlphaZero, which plays chess, and TD-Gammon, that plays backgammon. AlphaZero created a sensation a few years ago with its quality and originality of play, and created a lot of enthusiasm for the prospects of artificial intelligence and reinforcement learning. TD-Gammon is much older, about 25 years ago. And it also created a great deal of enthusiasm at that time. And it's just as impressive as AlphaZero, perhaps more impressive in some ways because it was the first of its kind. And stimulated a lot of research and motivation, including myself and John, got into the investigations that led to our neurodynamic programming book, motivated to a substantial extent by the TD-Gammon program. Now, these two programs are 25 years apart, but they involve a similar type of methodology, similar ideas. And both of them involve two algorithms. Now, a lot of people don't realize that there are two algorithms involved in these programs. One is the offline training algorithm, using neural networks to train a cost function approximation and also a policy network. And all of this is done with data, self-generated data, well before the program plays. In other words, this is the preparatory phase, the design of the algorithm, and then all of this is strapped into an online play algorithm which generates moves in real time against human or computer opponents. And it uses multi-step look-ahead, rollout, cost function approximation, and things like that. Now, both of these algorithms have strong connections to dynamic programming, the classical methodology of dynamic programming, the classical method of policy iteration, and also reinforcement learning type of approximations like neural networks and machine learning and the like. And what we're aiming to do here is to understand this methodology so that it applies far more generally. So we're going to focus on the connections with control system design, particularly MPC and adaptive control. I'm going to argue that the AlphaZero and TD-Gammon algorithms and MPC share the same ideas, the same fundamental architecture. And the framework that I'm going to introduce is very general, and it applies aside from continuous space, state space, and control space problems to discrete optimization, including integer programming. Okay, so I'm going to go first in these two algorithms, AlphaZero and TD-Gammon, and then interpret them in a more general setting. The online play algorithm in AlphaZero and other programs is based on approximation in value space. Sometimes people call it online tree search. What this algorithm is, what you see here in blue. The blue stuff here is the online play algorithm. But it crucially depends on the results of offline training at two places. A position evaluator, like a cost function approximator, given by a neural network in the case of AlphaZero, but in general it doesn't have to be. And also it involves a player, a base player that just generates controls in response to states. And the online play algorithm aims to improve on the base player by starting at the given position that you are. This is the initial state. Then at the current state, you generate all possible controls, and then you search forward for several moves through a look-ahead tree. Then you simulate the base player for some more moves. For every tree leaf here, you run the base player. You run into some other states over here, and then you approximate the effect of future moves by using the terminal position evaluator at the states. Now, once you have done that, then you go backwards. You back up this computation to the starting state, and basically by using backwards dynamic programming. And you calculate the values of the available moves at the root, and you play the best move. And then, after you select your move or your control, you move to the next state, and you do the same thing. Again, forward search, perhaps this look ahead with a base player, which we call truncated rollout. And you do the same thing and move forward until for an infinite number of moves or until a termination state is reached. Now, there are variations in this scheme. For example, AlphaZero does not have this middle portion. The middle portion enhances the look-ahead qualities of the algorithm, but AlphaZero uses such long look-ahead that it's not necessary to use this middle portion, at least in the public version. Perhaps they have tried it. AlphaGo uses a version of that. AlphaZero also uses a mini version of this middle portion, but it's not very substantial. TD-Gammon, on the other hand, relies very substantially on the middle portion. There's a difference between TD-Gammon and AlphaZero. TD-Gammon is a stochastic game, so that its tree expands very quickly, so you can't use long look-ahead. And this short look-ahead of TD-Gammon is supplemented by this truncated rollout portion. In fact, the name of rollout is due to Tesoro, the originator of TD-Gammon, and the name relates to backgammon, where you roll the dice, you roll out the game, and so on. Now, there are also similarities with model predictive control. In model predictive control, there's a minimization interval from the current state. This is called the control interval. And then in some versions of model predictive control, there's also some base policy that you run for a number of more moves in order to get to some terminal state. Altogether, this is called the prediction interval. And then there's also a cost function approximation at the end. So the architecture is remarkably similar, but there is a difference. In model predictive control, typically the state space is continuous, okay, like a Euclidean space, whereas in games, it's typically discrete, okay? But other than that, conceptually, the architecture is pretty much the same, and at some level, the mathematics are also very similar. So this is the online play algorithm, and now I'm going to go into the offline training. This takes place before you before you do any real-time operation of the system. And in AlphaZero, it is a form of approximate policy iteration using self-generated data, okay, the data, or self-learning as it's called. It generates a sequence of players, software that generates moves in response to positions. And the current player is used to train an improved player. And then the process is repeated. The current player gets you an improved player, and the improved player takes the place of the current player, and the process is repeated. Now, in policy iteration, we have two operations, policy evaluation and policy improvement. And the current player is evaluated by playing many games. The program plays many games against itself or against perhaps other opponents, computer or human opponents. And out of these games, we form some kind of an evaluation of its state, of its position. And that's the policy evaluation. And this is done using a deep neural network, a very sophisticated neural network adapted to the structure of chess and so on. It's called the value network. So that gives you a policy evaluation through the neural network and training. And now this current player is improved by using a form of approximate multi-step look-ahead minimization. It's a little peculiar. It's called Monte Carlo tree search. The policy improvement generates moves in response to positions, and these moves are used to train this improved player using another neural network, a policy neural network. Actually, in AlphaZero, the two are conflated together, but they can be thought conceptually as being different. TD-Gammon uses a very similar policy iteration algorithm for offline training with a value network. It uses a method called TD-Lambda, okay, one of the first methods in reinforcement learning, a very different method than the one that's being used in AlphaZero, but still the objective is to fit a neural network to values, okay? TD-Gammon does not use a policy network and does not use Monte Carlo tree search. Monte Carlo tree search is not fundamental, really. It's just an approximation to speed things up. And TD-Gammon replicates the functionality of the policy network by using the value network and one-step look ahead. So these two are very similar. In model predictive control, there is kind of a procedure like that, but a little different. There's less emphasis on repeated in policy improvements and policy evaluations. Okay, so now here are some major empirical observations. The AlphaZero program generates by offline training and deep neural network and zillions of computers and lots of computing time generates some player. However, that player is not very good. The online player plays much better than the offline trained player. So despite all the sophistication in the training, you're not getting really good quality of play unless you harness that offline trained player into a multi-step look ahead and online play. The online player is a phenomenal player, plays phenomenal chess. The offline trained player is relatively mediocre. So what this says is that one can improve on the results of offline training by using online play, and the improvement is significant. This is a fact. It's just very easy to observe, in fact, for people that play around with these programs, and also with computer chess. TD-Gammon plays much better with this middle portion than without the middle portion. Tesoro had two programs. One was in 1991 that did not have this middle portion. Went straight from one-step look-ahead or two-step look-ahead into a cost function evaluation trained with TD lambda, and it did not involve the middle portion. That 1991 program played at a subhuman level. It played pretty good backgammon, but not good enough to beat the best humans. In 1996, Tesoro introduced this middle portion to extend the look ahead, so to speak, and the performance of the program became much better and at a superhuman level. It could beat all humans, and also it played just extremely good backgammon. In backgammon circles, this program, the 1996 program, is viewed as optimal. They think it's optimal. It's not really optimal, but it plays so good that they measure everything else against that program as the yardstick. So now what we will do is try to explain these observations and get insight from them and motivate generalizations through the methodology of abstract Bellman operators, visualization, and there's a central load for Newton's method here. The offline player and the online player are connected through Newton's method. This is the same Newton's method that you know and love from calculus. It is applied to the Bellman equation of the dynamic programming problem that underlies this framework, and it's okay. It uses some embellishments, variations, depending on how you implement this methodology, including whether there is a truncated rollout portion or not. But it's Newton methods that ties everything together, and in my opinion, explains all the empirical observations over a period of 25 years. And now, here is in this figure, where is the Newton step? Well, you have a terminal cost function evaluation, and you have an online player, which has a cost function. The mapping from cost function approximation to the cost function of the online player is the Newton step. It maps a function into another function, and this other function is very close to optimal. And again, this is Newton's step on the Bellman equation, and it is just the very first portion of the look-ahead minimization. The Newton step is a tiny part, it seems, out of this picture, but it's the most important. All the other stuff is enhancing the starting point of the Newton step. It brings it closer to the optimal cost function, and from there, the power of Newton's method takes over and gets you very close to optimal. So you start with a cost function approximation, you improve it through this part, you improve it from this part except for the very first portion, and then the final step is the Newton step that ties everything together and does all the magic. That's what I'm going to argue. So these are the principal viewpoints of my talk. Online play is a single step of Newton's method for solving the Bellman equation underlying the problem. In the case of multi-step look-ahead and also truncated rollout, it is a Newton SOR step. SOR stands for successive over relaxation. It's really value iterations. value iterations with a policy or value iterations with minimization. And so in multi-step look ahead, what we have is start from a cost function approximation, enhance it through these SOR iterations, these value iterations, and then apply the Newton step at the end. Now, what the offline training does is it provides the start point for the Newton step through a terminal cost function approximation and also perhaps a policy to do truncated rollout with. However, the online plays the real workhorse. Offline training plays a secondary role, in my view, and there's a good reason for this. Offline training involves a lot of approximations with neural networks, and all of these degrade the quality of the starting point. It never gets you to what it would be, but because it involves approximations and neural networks. The online play, on the other hand, is an exact Newton step, does not involve any neural network approximations. And despite all you may think about neural networks having magical properties, they are not that magical, they involve errors. And these errors are the reason why the offline player does not play so well, and the online player plays much better. Now here's another insight. Okay, the offline training can be done with many different methods. Temporal differences methods, aggregation methods, linear programming. There's many, many different methods for offline training and policy, approximate policy iteration. And these differences affect the starting point, but these differences are washed out by the superlinear Newton step. People in numerical analysis that have worked with Newton's method know very well that if you are within the sweet spot of Newton's method, variations within the sweet spot don't matter. Just in one step, you zoom into the optimal, and that's that. On the other hand, if you're far away, outside the region of convergence or outside the sweet spot of Newton's method, then it may not be as good a method. On the other hand, once you are close to the your starting point of the Newton step is close to the optimal, all differences between offline training methods are washed up. And I had this experience when I started working in this field 25 years ago. I would try various different types of offline training methods. They produced different results. I could see that the results were different, but once they were strapped into an online look-ahead minimization, the differences disappeared. They were very close, too close to understand. And I have now come to understand that this is the reason, that once you get within the sweet spot of Newton's method, then differences in training and how much data you collect, how you collect it, and so on, they don't matter. Okay, there is a cultural difference that we will aim to bridge. There is a reinforcement learning AI type of research in this area, and there's also control type of research in this area, based primarily around model predictive control and also adaptive control. Now, the AI research is focused largely on offline training issues. How do you collect data? How do you use it? How do you do the training? How do you select the neural networks? And so how you design them, and so on. On the other hand, model predictive control is focused primarily on online play and also issues of stability. You'd like your online controller to be stable. That's of paramount importance in control theory, although in artificial intelligence, this subject is not really addressed almost at all. By bringing together online play and offline training, we aim to bridge the gap between these methodologies. Adaptive control is an important subject in control theory. It involves systems whose parameters change over time. As the system parameters change, it is possible to try to estimate them online. And this is what's done in a large portion of adaptive control methods. Even though the Bellman equation, even when the the model changes due to online estimation, the Bellman equation also changes. On the other hand, you still have a Newton step, which is exact. And as long as you perform the Newton step, then the performance of the overall system is still very good, because the Newton step is very powerful. The final thing I want to impress on you is that all of this applies in great generality. All of this is couched. The insights, the mathematics, the visualizations, all of this is couched on a methodology of abstract dynamic programming that views dynamic programming models in generality, with arbitrary state spaces, arbitrary control spaces, stochastic problems, deterministic problems, hybrid systems, multi-agency, minimax. Dynamic programming is a very, very general methodology, and it applies to a very broad classes of problems involving spaces that are arbitrary. Our insights and analysis will be based on abstract dynamic programming and therefore apply universally. They apply in a very, very broad class of problems, including games as well as control systems, integer programming, and the like. Okay, so here's my outline. Excuse me. Okay, in the way of introduction, I'm going to set the stage with some discounted and undiscounted dynamic programming models over an infinite horizon. Everything applies to finite horizon as well, but I'm going to focus on infinite horizon. Then I'm going to introduce abstract dynamic programming concepts like Bellman operators, Bellman equations, non-abstract setting. Introduce visualization of online play as a Newton step. Discuss stability and the region of stability and how we visualize it and what we can do to improve it. Then I'm going to provide visualizations of policy iteration and a single iteration version of policy iteration called rollout. It's the same rollout that I mentioned earlier. Then I'm going to discuss adaptive control, and I'm going to discuss an application to the Wordle puzzle, the New York Times Wordle puzzle. It can be formulated as an adaptive control problem, and it lends itself very well to the use of rollout. Finally, I'm going to say a few things about discrete optimization, integer programming, assuming I have the time. Okay, so let's take this as a starting point. Infinite horizon problems involving a system that has a state xk at time k. The system moves from xk to xk plus 1 through a system equation that depends on state, control, and a random disturbance, a random variable wk, which is a stochastic system. Corresponding to this transition from xk to xk plus 1, there's a cost, which is also random because it involves wk. It's also discounted with an alpha factor, which is less or equal to 1. And we are interested in policies, stationary policies in particular, that map states into controls through this function mu and satisfy some control constraint for all x. Now, once you have chosen a policy, the cost of the kth stage is given by this. The control applied is this one here. And the cost of the policy is the sum of the stage costs over an infinite horizon. So what we have here is for any run of the system over n stages, this is the sum of costs that's generated. It's a random variable because of the presence of wk. We take the expected value of that. This gives us a number. And then we take the minimum over the number of stages. And this gives you a number corresponding to the policy mu and an initial state x0. So this is a function of the initial state, and it's the cost function of mu, of the policy. The cost function of the policy is this. It gives you the expected cost of the policy over an infinite horizon starting from this state. And the optimal cost function, which I denote by J star, is obtained by minimizing over all policies mu. It's again a function of the initial state. And I have in mind three primary classes of problems. One is discounted problems, where alpha is less than 1 as g, the cost per stage, is bounded. And this is the nice case. All the results that you would like to hold. All the analysis that you would like to do eventually come through and can be done relatively easily. This is the nice case of infinite horizon dynamic programming. Another class of problems are stochastic shortest path problems, where there is no discounting, but there's a special termination state which is cost-free. Like games, for example, have a termination state, which is not known perhaps a priori, but this termination state keeps the cost finite. And these problems admit a relatively nice analysis, not quite as nice as discounted problems, but there is the results that you would like to hold once you make the proper assumptions and you view the problem properly. Finally, there is the control MPC type of problems, which are, for the most part, deterministic. People look at stochastic versions of MPC, but the starting point for MPC is deterministic problems. Positive cost, to provide an incentive to go to the termination state. The termination state has zero cost. Non-termination states have positive cost. So this provides an incentive for the control to drive the system towards the termination state. These problems do not have quite as nice theory as the other two. And they involve a lot of pitfalls, but they have been studied a lot and people know how to deal with them by now, and they're quite well understood. Okay, so in this slide I'm going to give you a quick rundown of the theory of dynamic, infinite horizon dynamic programming. The principal fact is that J star, the optimal cost function, satisfies Bellman's equation. Bellman's equation is what you see here. It's a scalar equation for every x. So it maps J star into something else, and this equation says that J star is a fixed point of this equation here. In some cases, it is the unique solution of Bellman's equation, but not always. That's why I put this question mark here. And then there's the optimality condition. If you knew J star and you were to do a minimization here for every state, you would obtain a policy. That policy is optimal, okay? Not always true, but mostly true. Certainly true in discounted problems. Then we have algorithms. The value iteration algorithm generates a sequence of cost functions which you hope would converge to J star. And what the form of it is what you see here. Start with some J0, you generate J1 by doing this minimization involving the right-hand side of Bellman's equation with J0 replacing J star. From J1 you obtain J2 and so on, you obtain a sequence. J0 is more or less arbitrary, okay, but there are some exceptions here. And you expect to converge to J star. It's one of the principal methods of, principal computational method of dynamic programming. And the other main computational method is policy iteration. Value iteration iterates on value functions. Policy iteration iterates on policies. It generates a sequence of policies, mu k, and their cost functions, starting from a more or less arbitrary initial policy. And it involves two phases, two steps, policy evaluation and policy improvement. Now, the typical iteration starts with some current policy and generates a new policy. First, by evaluating the current policy, perhaps with approximations. For example, a finite number of value iteration steps. Okay. And then after you have this evaluation, you do a policy improvement where you stick this evaluation into this minimization and you obtain a new policy for every state. So from mu, you get mu tilde, and then mu double tilde, and so on, generate a sequence, and you hope that this will converge to an optimal policy and the optimal cost function. So that's the theory in a nutshell. And now, where does reinforcement learning come into play, and what does it do? If we knew J star, then we could minimize in the right-hand side of Bellman's equation to act optimally at any state. We would do this minimization online. Now, the problem with this is that we don't know J star, and in approximation in value space, we replace it by J tilde, some kind of approximation, obtained by offline training, obtained by because somebody gave it to you. Somehow you have this J tilde, and you stick it in here, and you generate controls online. This is one-step look ahead, where you try to balance the cost of the first step and the future as evaluated by J tilde. In multi-step look ahead, you do much of the same. At the current state xk, you look L steps ahead, L greater than 1. And you try to minimize the sum of the cost of this first L steps, and then add the cost of the future as evaluated by J tilde. Now, this minimization can be done by L-step dynamic programming, and it will give you an initial control to apply at xk and policies for the remaining stages. And what you do at xk, once you have solved this problem, you use uk, the first control out of this sequence, and you throw the other stuff away. And then you go to the next state and do the same thing, and so on. Each step involves a one-step dynamic programming calculation or an L-step dynamic programming calculation. Whether you do one-step or multi-step, these operations define a policy, this mu tilde policy at xk, which gives you the minimizing uk. This is the greedy policy. I'm going to be referring to this as the one-step look-ahead policy or multi-step look-ahead policy or just greedy policy. So we have J tilde that we start with, and we end up with a greedy policy mu tilde. I'm going to be using this notation throughout the lecture. And the key new fact here is that J mu tilde, the cost function of the greedy policy, is the result of a Newton step to solve Bellman's equation starting from J tilde. In the case of one-step look ahead, and starting from some J tilde enhanced by a number by this dynamic programming operation through a Newton SOR step. And because this is a Newton step, it has superlinear convergence. In other words, you start with an error, J tilde minus J star, your approximation error from the optimum. And you end up with a new approximation error, which is the cost of the greedy policy. Now, this new approximation error is tiny relative to this. You may start with a big error and end up with very small error, and this is guaranteed if J tilde is close to J star. It's within the region of convergence, and so to speak, the sweet spot of Newton's method where quadratic convergence and superlinear convergence takes effect. So that's the key thing, and that's the point where I'm going to base everything, including my visualizations. Now, to understand all this, we need to look more abstractly through abstract dynamic programming and introduce in a more general setting Bellman equations and Bellman operators. And there are two Bellman operators here. Now, I've written an abstract dynamic programming book in 2013, and the third edition, the second edition was substantial revision. The third edition, not a very substantial revision, but still a revision. And you can find this in the internet. There's a free PDF available. And the idea in abstract dynamic programming is to abstract the essential elements of the dynamic programming theory and encapsulate them within these operators, the Bellman operators. And in the context of the discounted problem that we have been considering here, there are two Bellman operators. For a given policy mu, the mu Bellman operator is simply the right-hand side of Bellman's equation for the policy, and the min Bellman operator is obtained by minimization of the mu Bellman operators over all policies. Now this is an operator in the sense that it takes a function j and produces another function, t mus of j. Similarly here from a function j we obtain another function t sub j, and the Bellman equations that hold in the context of dynamic programming say that for the policy mu, j mu is a fixed point of the mu Bellman operator, and j star is a fixed point of the min Bellman operator. So there's a shorthand notation which is very nice here. And however, just let's try to discuss these operators a little bit. Okay, here I'm going to assume that t and t mu map into real valued functions. That's not necessarily true, but we are going to assume it here for the purpose of this talk. For any fixed state, these are functions of j. So they live in a continuous space, in a function space, even if the problem is discrete or has a discrete state space. Another important property is that t mu is monotone. If I increase j here uniformly for all states, t mus of j also increases monotonically. Moreover, the t mu operator is linear, okay? Because the expectation operation is a linear operation. The t Bellman operator is not linear, but is obtained as minimization of linear operators, so it is concave. In other words, for any state x, tj of x is an honest-to-goodness concave function of j. Moreover, t is also monotone. If you increase here j, t sub j will also going to increase. On the other hand, these operators are very complicated. Suppose that you have only two states. You have a Markov decision problem with only two states. Then the j vector is a vector in R2. The tj vector is also a vector in R2. So to construct a graph of this operator, you need a four-dimensional space, which you do not have. So that's a problem with visualizations. If you go to an infinite dimensional state space, t mu and t are infinite dimensional operators, and they map infinite dimensional function space into itself. So it's very difficult to visualize them. Our approach here is to use visualization along one-dimensional slices of the graphs of the operators. Now, this does not provide proofs, mathematical proofs. On the other hand, it provides a lot of insight and food for thought and conjecture, which you have to verify by using mathematical analysis. So that's the line that we're going to follow here. Visualize and conjecture based on one-dimensional slice visualizations, and then verify through rigorous mathematical analysis that the results of the insights from visualization are indeed correct. So I'm going to be using one-dimensional slice visualizations, or one-state visualizations, if you will. And let's visualize the mu Bellman operator in one dimension. Here's the operator. It's linear and monotone. And the mu Bellman equation is what you see here is this fixed point equation. So here's the graph that I'm going to be using for visualization here and in future slides. On the horizontal, we have j, the cost function. And on the vertical, we have t mus of j. And the graph of this operator is linear, what you see here. It's this blue line here. It is monotone, and it's linear. And how do we visualize the solution of this fixed point equation? Well, we have to make the right-hand side equal to the left-hand side. So the solution is the point of interception between this and that. And this is the cost of mu. It's the solution of the fixed point equation. Okay, so now let me go to the min Bellman operator. it is what you see here, minimization of all these linear operators. And so what we have here is the graphs of the linear mu operators, and we take the minimum of those to obtain the graph of the min Bellman operator, which is this red curve here. So the red curve is the envelope, the lower envelope of these linear operators, and it's concave. So suppose we are at J tilde and we want to find T's of J tilde. How would we do that? Well, we go up here, we find the points of interception with the blue Bellman operators, and then we go down and find the minimum of all these points of interception. It's this point here. And if we consider, now this is the greedy policy at J tilde, right? It's obtained by minimization in the right-hand side of Bellman's equation, and it has a certain graph. Now that graph, because of the concavity of the red operator, is a tangent. It involves a linearization of the red operator, and the greedy policy evaluation is obtained by finding this point of interception, drawing the tangent, find the point of interception here, and this is the greedy cost. So from J tilde, we obtain J mu tilde. And I'm going to argue that this step here is a Newton step. Okay, so let me go into, before I do that, let me also show you the visualization of the value iteration method. Generates a sequence of functions by applying the T Bellman operator successively. And it starts with J tilde, then it goes up to the red curve to obtain T's of J tilde, which is J1, reflects this point along the 45-degree line to obtain J2, then J3, and so on. And that's the way it works. The results of value iteration is obtained through this staircase construction, and as you can see from this figure, there's a good chance that Jk converges to J star, but the convergence depends on the slope of T. If T is a contraction, then things work out. If it's not a contraction, then you may have some difficulty. Okay, so now let's get back to Newton's method and its visualization. Let's look at Newton's method in general for solving a generic fixed point equation. So T here is not related to dynamic programming. It is just a generic fixed point equation, which I have here indicated in red. This is the graph of T. Now, Newton's method generates a sequence of iterates, Jk. At the current iterate, what you do is you linearize this operator at Jk, solve the linearized equation. In other words, replace Tj by this linearization and solve this fixed point problem here. Then you obtain Jk plus 1, and that's the way Newton's method works. Then, once you are at Jk plus 1, you linearize again, intersect with the 45-degree line, obtain Jk plus 2, and so on. Now, that's the way you learn Newton's method in calculus. On the other hand, typically in calculus, always in calculus, you assume differentiability of T. So you can use first-order Taylor series expansions, gradients, and the like. Do we need differentiability? Well, the answer is no. And in fact, this is important because in dynamic programming, we are not guaranteed this differentiability. Concavity of T is enough, and this has been known since the middle 70s. all you need to do is linearize appropriately Bellman's equation, or the mapping T, using perhaps subgradients. And this is what happens in our dynamic programming context. So from the general type of Newton's method for the generic fixed point equation, let's go back to dynamic programming and look at one step look ahead and the Newton step interpretation there. What we have is a cost function approximation J tilde. The greedy policy, as I argued earlier, is obtained by forming a tangent to the graph of T. This defines a linearization of Bellman's equation, and the solution of the linearized problem is precisely the cost of the greedy policy. So from J tilde to J mu tilde, I go through a linearization process that's exactly the same as for Newton's method. This is the Newton step corresponding to J tilde. So that's a key insight on which everything is based, and there are some important ramifications. The first is that the Newton step smooths out starting point variations. Okay, so if you change a little bit J tilde, the difference here is going to be tiny. You're still going to be very close to J star. The other thing is that locally, the error decreases very differently than what current theory suggests. Current theory is a global theory of error bounds that's conservative and bears very little relation to reality. In reality, what happens once you get close to the optimum is a very different behavior of the error. It decreases superlinearly and much, much faster than the current theory predicts. Now, if you have multi-step look ahead, it's a similar picture that occurs. In multi-step look ahead, you precede the Newton step with a number of value iterations. So you start with a cost approximation J tilde, do a number of value iterations, 2 in this particular case, go up to this point, and at that point you apply the Newton step and obtain the greedy policy and its cost. So from J tilde to J mu tilde, there's a Newton SOR step. 2 value iterations first, and then a final Newton step. Now, the Newton SOR method still converges very fast, and faster, in fact, than the pure Newton method, but it's more time-consuming. That's the basic trade-off. Okay, just a short interruption here. Well, it's 4:59, and we started late, and I'd like to shorten my talk, and you can find the slides on the internet. And what I'd like to do is okay, I won't have time to talk about the region of stability. Incidentally, there's a 2-hour version of this talk that's on the internet. And it's pretty much the same as what I've given here, with a few exceptions. And you can see this talk on the internet. Now I'll have to shorten this talk. Maybe I'll just record the full talk in Zoom and put it up on the internet. But I don't think I can finish this talk in the amount of time that we have. So what I'll do is I'll skip stability and the region of stability, the regional convergence of Newton's method. Then rollout is simply a Newton step starting from J tilde equals to the cost of some policy. And there are some important advantages to rollout. And there's also policy iteration is just a repeated rollout. Starting from a stable policy, it produces a sequence of stable policies. Incidentally, policy iteration and its interpretation of Newton's method was actually invented here at LIDS. It's not LIDS really, it was Electronic Systems Laboratory at that time. In 1968, there was a thesis by David Kleiman, a student here, who developed this connection of policy iteration and Newton's method for linear quadratic problems. David Kleiman was a student of Mike Athens. There was a lot of research in this area at that time on optimal control, beginnings of optimal control here in our laboratory. And Kleiman's work was followed up by several other people, and the interpretation of policy iteration as Newton's method is well known in control theory. On the other hand, the new part is the interpretation of approximation in value space in terms of Newton's method and the insights that you can get from that. Okay, there's rollout with approximate policy evaluation, truncated rollout. Then there's a theory for linear quadratic problems, a familiar class of problems where you use Riccati operators instead of Bellman operators. And this is somewhat more insightful in the context of linear quadratic problems. And the Riccati equation has a similar kind of, Riccati operator has a similar kind of graph, but it involves the restriction of the Bellman operator to the subspace of quadratics. This kind of interpretation is very nice because you can program it in MATLAB, and within an hour or two, you can see a lot of things that and verify some of the things that I'm talking about here today. It's a very nice way to visualize what's happening within the context that I'm describing. Let me say just something about this question. I get this question very often. In the end, we want to produce some kind of an online player which is good. Well, suppose that we got that through Newton steps, multi-step look ahead, whatever, what have you. Why can we not train a neural network to emulate this online player? And in this way, we're going to be using approximation in policy space. Get some good controller and then approximate through a neural network. Now, this viewpoint, I argue, is flawed. It is a mirage that you're going to get a good controller this way, because this transcription from the online player, which is good, to one represented by a neural network, it does not involve an exact Newton step. It involves approximations that are introduced by the neural network. So you're not going to get the advantage the full advantage of approximation in value space and one-step or multi-step look ahead. And there is an example here that you can find in the book, and illustrates the difference, what happens if you use the Newton step and when you don't use the Newton step. There's a big difference in performance. Okay. I'm going to spend a little bit of time on adaptive control because I want to say something about Wordle, which was a project that was a lot of fun for me and a couple of my students at ASU. Adaptive control involves a system whose parameters are changing over time. And what we often do here is we estimate these parameters from the system as it is operating. We obtain data, estimate the model of the system, the change parameters, and we feed them into an adaptive controller which adapts its control accordingly. And the classical methodology of indirect adaptive control is based on the reoptimization. You get new parameter estimates, you reoptimize the controller. And you keep going like that. On the other hand, this reoptimization may be time-consuming. Okay? In linear quadratic problems, perhaps it's not time-consuming, but for other problems, it is quite time-consuming. So it is a problem. But here there's a faster alternative, which I argue is almost as good. Do indirect adaptive control by using rollout in place of reoptimization, and use a Newton step, in other words, instead of reoptimization. And the result is just as good almost. And it capitalizes on the fast convergence of the Newton step and also provides insight why model predictive control has worked so well with adaptive control situations. So I have a computational example here. adaptive reoptimization and adaptive rollout with a Newton step is almost as good. And if you use a base policy, a fixed policy, without a Newton step, then you miss a lot in terms of performance. Now there's an alternative adaptive control formulation which dates back to the 70s and reformulates the problem into a POM-DP, a partial state information problem, where the unknown parameters, which I call theta, become an initial state, and it's part of an augmented state that's partially observed. And you estimate this state by forming over time a belief state, which is the probability distribution over the unknown parameters given the information that you have collected up to time k, which are the states of the system. And there's a Bellman equation for this POM-DP, and I'm giving it here. It involves the cost function as a function of the information available up to time k, and this is the information available at the next state, which depends on the unknown parameter. And also there's the belief state that comes here, this probability distribution. And now again, J star is very difficult to compute. And in approximation in value space, we can use an approximation J tilde in place of J star, which depends on the unknown parameter under a clairvoyant assumption that you know theta, the true value of theta. So, and you minimize over UK and you obtain a greedy policy, and there are a couple of options here. The first one has been investigated extensively in the 80s, and it involves interesting mathematics and interesting ideas, and there are some pitfalls in this approach which people have investigated. And in this approach, you use as J tilde the cost function of the optimal policy under the clairvoyant assumption that you know the value of theta. And this may be easy to calculate, and you stick it in here in place of J star, and you obtain an adaptive control policy. The other possibility is to use rollout in place. So J tilde I is the cost function of some known policy, again under the clairvoyant assumption. And this is what we have used in the Wordle puzzle. Now, what does Wordle? I presume that most of you know what Wordle is. Just about anyone I talk to knows or is a dedicated player of the puzzle. It appears in the New York Times every day. A lot of millions of people play it every day. I never played it myself. I had a hard time understanding the rules in the beginning, but anyway, we were able to model this as an adaptive control problem where the unknown parameter is the unknown mystery word. Here we're trying to find some mystery word that's chosen with a uniform distribution from some list of mystery words. And then you try to guess that mystery word through guesses drawn from some list of guess words. And so it's basically the controls are these guesses that you choose sequentially, and you're allowed a number of guesses, and these words have 5 letters and number of guess words in the over 10,000 words. So it's a substantial list, substantial number of controls that you can choose from. So now this type of problem, together with other search problems of finding some hidden object by using observations, is part of this formulation here. We have applied rollout. Now the details I'm not going to be able to give you. Here are my collaborators, and we are going to have a paper in a few weeks from now. I'd like to show you the results. What you see here is different opening words. The best opening word is this salad. It's a strange word, and I had to look it up. It's some kind of a strange hat, okay? It turns out to be the best opening word. The best initial guess turns out to be this salad. And what you see on the vertical here is the average score, the average number of guesses that you expect. by, okay, it's average because you don't know the mystery word. It's average over the initial uniform distribution of the mystery word. And the optimal is, people have calculated the optimum with days of computation. It's a gigantic dynamic programming computation, but people have done it. Days of computation with parallel computing systems and the like. And the optimal is 3.5084 on the average number of guesses needed to find the mystery word using this solid initial word. And there are a little higher numbers for the other initial words. So the optimum is right where you see this horizontal, but a little higher. It's around 3.51. And we have tried rollout with 3 different base policies. And there are 3 base policies here. One is this maximum information gain. All of these base policies have been suggested in the literature, by the way. There's the blue stars give you the performance of this, the performance of this maximum information gain policy for these opening words. And another policy is this yellow policy. And another policy is the red policy. And what you see here, the circles, are the performance of the rollout policies. Now, you won't see any red stars. The reason is that the performance of this policy is off the chart, okay? This is a really bad policy, it turns out. It's at least the way we have implemented it. It's like 5.8 or something. It's way, way higher. On the other hand, the other two, the blue and the yellow, are fairly close to the optimal. Now, the rollout gives you uniformly good results, much better results. The best that we get is 3.5231 versus this, which is the optimal. In other words, we hit the optimal number of guesses on the average within less than 1% additional number of guesses. And moreover, we get the online answer within seconds, like 1 second, 2 seconds, 3 seconds. If you were to find the optimal, and all of this, by the way, are bunched up together, which shows how the Newton step washes out the performance difference of the various base policies. And the other point I want to make is that if you were to change the Wordle puzzle a little bit, increase the size of the mystery list or the guess list, or instead of having 5-letter words, consider a list of 6-letter words or 7-letter words, then the rollout approach applies and still solves the problem within seconds, but finding the optimal approach would be entirely impossible, outside the realm of possibility. So, okay, so I was excited about this research project. I wanted to let you know about that. And I'll skip integer programming. And I'll quickly go through some of this. There's much to be gained by using online play on top of offline training. This is the principal message I want to convey. The role of Newton's method is central here, that can guide both analysis and algorithmic design. The cultural divide between AI and control can be bridged through this synergism of offline training and online play. And then finally, all of this is very general. It applies to arbitrary state and control spaces through the formalism of abstract dynamic programming. So all in all, I think there's an exciting journey ahead, and I hope that we will all be participants. Thank you very much for your attendance, and sorry for taking a little longer than expected.